learning about all the different programs and opportunities that are out there. I was also lucky to be at NASA Johnson Space Center, the home of space exploration. We had the opportunity to learn and be involved with various human space exploration efforts, including seeing various habitats such as lunar and Martian rover, various research labs, and also got to meet various astronauts. Now, at Florida State, I study how they adapt when they travel into space. So I've shared a little bit about my personal journey, and now we're going to switch gears a little bit and chat about the James Webb Space Telescope pictured here. Now, with this visual, I'm curious, are there any specific elements of the space telescope that anyone may be interested in sharing their thoughts or perspectives on what they may be? Is anyone familiar with the Parkes telescope? Has anyone used the telescope before? Yes, no?
Yeah, maybe I can give a perspective.
Great. And who is speaking?
Yeah, my name is Rafi. You can call me Rafi.
Hi, Rafi.
Yeah, actually,
thanks for. Go ahead.
Yeah. Actually, I'm very interested in its mirrors. So as you can, as you all know, that JWST is currently the biggest space telescope in terms of its also mirrors, 8-meter telescope, 8-meter telescope. Then I think compared to Hubble, this space telescope will be comparatively very powerful than Hubble, because Hubble, as long as I remember, its mirrors, mirror's diameters is about 4 meter, 2 meter. I forget, but yeah, JWST is far larger. The mirror is far larger than Hubble. So in terms of observing time, is in terms of the exposure time for observing the objects, it will be much faster than the Hubble. So yeah, its mirror is very interesting for me. So and then because of its large size, also it needs to be fold to be carried to the space, right? So I think it requires a very advanced technological engineering to be able to unfold such large mirrors like the JWST had. So yeah, I'm very interested in the mirror.
Thanks, Rafi. And yes, I'm glad you brought up the Hubble Space Telescope. That is a great example of a telescope to compare James Webb Space Telescope with. And I'm glad you brought up mirrors as well. Mirrors are a critical element to telescopes. And we'll talk about a bit about mirrors some more. But would anyone like to share their thoughts as to why mirrors may be important for any kind of telescope, whether James Webb Space Telescope or the Hubble telescope or telescopes they may use in your backyard? And if not, that's okay. We're going to find out why mirrors are so important. And to go into a little bit more detail of the James Webb Space Telescope and mirrors and how it's designed and engineered, there are it's a spacecraft. So not only is it a telescope, but it's a craft that has to travel in space. So there are various control systems that provide ways for the telescope to travel in space, propulsion, so to speak. And in turn, that requires the telescope to also uh, uh, required to be have a power source. So this power source is provided through a solar power array built in part of the James Webb Space Telescope that can be folded open and closed depending on the mission state and configuration needed. In turn, there's also a sun shield to protect the telescope from light and heat, from overheating essentially, because there is very specific electronic equipment that captures information from the mirrors that includes all the cameras and science instruments that we'll talk in greater detail about as well. And then, of course, we have the mirrors. We have two mirrors. We have the primary mirror that Robbie had mentioned that includes 18 hexagonal components that are that exist to capture infrared light. And there is a secondary mirror, however, that reflects gathered light from the primary mirror onto the scientific instruments. So James Webb Space Telescope actually captures light by its primary mirror, which then is reflected onto this secondary mirror, which then reflects information back here onto a science instrument module. So now I'm going to actually switch screens and share a video. So one moment. Okay. Okay, I'm going to play a video now. Can you all see it in the video?
Oh, we can't hear any sounds.
There's no sound yet. I think you have to allow to share the audio as well.
Yes. Okay, let me play from the beginning. How about now?
The James Webb Space Telescope is one of the most complex and sophisticated scientific instruments ever built. A joint mission between NASA, ESA and the Canadian Space Agency, it's seen here folded and packed for launch in a clean room at Europe's spaceport in Kourou, French Guiana. Operating 1.5 million kilometres from Earth, the observatory will unfurl in space to reveal a 6.5 metre wide primary mirror made up of 18 individual hexagonal segments, a smaller secondary mirror and a giant multi-layered silver sunshield. The engineering is an impressive example of human ingenuity, but when it comes to science, Webb promises to reveal the basis of our very existence.
The origin of Webb is the search for our origins. We want to find out where the first galaxies formed, how they formed when they started making their stars in the very early universe not long after the Big Bang. And to do this, Webb uses its big mirror and its infrared vision to look into these really early days, observe the light from these galaxies that's been traveling to us for billions of years, and it shows us these galaxies, how they were billions of years ago.
In orbit now for more than 31 years, the Hubble Space Telescope has already transformed our view of the cosmos. It's revealed the accelerating expansion of the universe, the birth and death of stars, the evolution of galaxies and storms on Saturn and Jupiter. But Hubble primarily detects visible light, the wavelengths we see with our own eyes. By viewing in the infrared, Webb will be able to give us a new perspective on the universe. To capture photons of light that have travelled across space for billions of years, the new telescope is loaded with innovative detector, optical and cooling technologies.
The telescope itself has to operate at a temperature of minus 233 degrees Celsius. And that means that all of the systems on board have to be able to cool into space behind the giant sun shield. And getting that sun shield, the size of a tennis court, to unfold into space and shield the telescope has been one of the biggest engineering challenges solved along the way.
Webb's 4 scientific instruments include MIRI, a mid-infrared camera and spectrograph. This involves a consortium of European institutions led from Scotland. And NIRSpec, a near-infrared spectrograph, which is led by ESA.
It's very important because it will allow us to analyze the light of the astronomical objects we will observe. These instruments will split the near-infrared lights from the astronomical object into its components. And this is very useful to scientists because from that they can understand the physics of the objects they are observing, what are the temperature, the elements, the physical condition, and therefore we can understand what's going on the objects we observe.
So the James Webb Space Telescope will not only be able to view newly formed galaxies and stars, but determine what they're made of, and in the case of planets, even whether they have atmospheres capable of supporting life. It's taken more than 30 years of planning, designing and construction to get to this point, but it's going to be worth the effort. Like Hubble before it, Webb has the potential to transform our view and understanding of the universe.
Okay, great. I hope you all were inspired by that video. It's incredible to consider how it's taken, yes, 30 years for development of James Webb Space Telescope. Now we are less than a week away from it finally being launched. So it's incredible to see in a very short period of time some details with regards to the James Webb Space Telescope and how it works, and how it will increase our knowledge of the universe in a way that has never been done before. One moment as I... So we're going to take a, based off of what we've learned so far, we're going to break for just a minute or so. And I'd like for y'all to think about the question, if you had the opportunity to design a space mission, what may it be? Would it be something similar to James Webb Space Telescope, or would it be something different? Recently, we had a few additional launches, such as Lucy mission, which is a mission that's going to Jupiter. And then we also had the DART mission that is going to an asteroid binary system. So there are many different types of space projects. Please feel free to share your own thoughts behind a space mission, either in the chat or share by unmuting your mic and giving us some examples of what you may think of your own space mission and what it may be.
Maybe I can share my point of view again. So yeah, actually, right now I'm an astronomy student, graduate astronomy student at Japan, and my research field is exoplanets. So if I had the chance to design a space mission, that it would be space mission from for exoplanet observations, especially its atmosphere, like the James Webb Telescope did. So I will be design a space telescope that have a spectrograph, a really high resolution spectrograph, maybe R over 50,000 or more, to detect any biosignature in exoplanet atmosphere. So through transmission spectroscopy, the light from its stars pass through the planet atmosphere and imprint the presence of molecules in the spectrum. So with high resolution spectrograph, we can detect such footprint from the molecules. So I will be designing a space telescope that could harbor an instrument, specifically the spectrograph, like the NIRSPEC did. So as you know, the JWST has instrument namely NIRSPEC, near infrared spectrograph, that could detect even the faintest footprints of molecule in planet atmosphere. So yeah, it will be space mission that observe exoplanet atmosphere. Yeah.
Thanks, Josh, for sharing again. Would anyone like to share their another space mission project? Okay, well, think about maybe this question and we'll return to it later on in the presentation. So let's talk a little bit about what JWST, James Webb Space Telescope, will observe. So one, it's a telescope, and it will utilize light to search for light from the first stars and galaxies that formed in the universe after the Big Bang, to study the formation and evolution of galaxies. And in turn, galaxies are made of stars, which also have their own formation, development, and life cycle that JWST will observe and study. And in turn, some stars may have planetary systems around them. So JWST will study that as well. And then in turn, based off of those planetary systems, will add to our search for life and observational life in our universe. And for example, here are some images taken by Hubble, actually, where in these two images are different spectra of light, where this is the top is ultraviolet, high energy, and then this is the same picture, actually, but in a different wavelength of light, the wavelength being infrared. And Hubble had the capability of measuring multiple wavelengths, ultraviolet and infrared, though was limited in terms of the distance. What James Webb specialized in is infrared wavelength, though is and in turn we'll be able to see a much further distance and high resolution than Hubble did. And to describe a little bit about this in more detail, this is very much connected with mirrors. Mirrors are what capture and reflect the light to be focused in a way that telescopes can magnify the light. And telescopes are designed to and can capture light across different types of light, as light is made from photons that have different wavelengths. And wavelengths can be all the way as small as 0.1 nanometers to a kilometer in size. And for example, radio waves are actually light at very high wavelength. And visible light, the light that we see, is light in a wavelength between less than a micron and more than 100 nanometer. And it's just a very small region of the wide range of light wavelengths. Now, the previous image showed a ultraviolet image, and that is a wavelength smaller than light. And that includes gamma rays and X-rays, and generally are blocked here on Earth in terms of being able to see. But then there are special telescopes that are in space that specifically search the universe and capture light with the Kepler Space Telescope and search for exoplanets being an example. Then we have JWST, which will capture light in infrared, which is larger wavelength than light wavelength, but smaller than radio waves. And both gamma, X-ray, ultraviolet, infrared light is actually blocked by our Earth's atmosphere. So that's why we can, the Earth's atmosphere also serves as a filter of light. So light that we can see, visible light, can be observed here on Earth without with some atmospheric distortion. But infrared light and gamma, X-ray, ultraviolet light from universe can't be seen. So that's why we have to have these telescopes travel into space. So another breakout session here. So if you could, I mentioned that we observe many features in space here on either here on Earth or through projects that we send in space. And in turn, if there may be a specific object that you may be interested in studying in space, what may it be? And that could include planets, galaxies, comets, nebula, black holes. Kind of think of yourself as a Guardian of the Galaxy crew member, traveling across the universe and searching for a specific object of interest to you. Okay, so take a few moments if you'd like, and welcome to share your object of interest in the chat as well. Awesome. Thank you so much for sharing, everyone. So I see Planet 9 from Peter, Groot from Sirius, AGN from Donnie, Black Holes from Kelly, Black Holes as well from Ferdinand. Facia has mentioned asteroids. Rio has mentioned a specific type of black holes, intermediate mass. Okay. Devendra has mentioned pulsars.
I
PD,
wanna study on black hole.
Ursa just mentioned black holes, rogue planets, exoplanets, so stars. Thank you for sharing. Quasars, supernova. So yes, there are many, many different space objects that could be studied, and we'd love to see some of you all study these in the future. So let's talk about the James Webb Space Telescope in more specific detail. Okay, so we talked a little bit about this previously, where the James Webb Space Telescope includes various components, including a various mirrors, a sun shield, and then additional components such as a spacecraft bus, which serves as a way to control the, we talked about the spacecraft control mechanism, a way to travel, but also control how the telescope is performing. And it also includes a radiator system to release heat, and many additional components, as this is a very complex system that has many different parts. One that Ravi had mentioned previously was the mirror system. So here's a example of the mirrors of scale of an individual compared with Hubble's primary mirror. So this individual is standing next to a Hubble-sized mirror, but the same size as an individual. And now all the James Webb Space Telescope components, mirrors put together, are this size compared to the Hubble mirror. You can see they are significantly different. Even one of these hexagonal elements is approximately the size of the Hubble mirror. Putting together, it's significantly larger than the Hubble Space Telescope. And in turn, with it being larger, can capture more light. And the mirrors are built and put together at a NASA center in the United States called NASA Goddard. And here you can see it being, it's been assembled. And here are some engineers actually performing some testing on the mirrors to polish them. So make sure they are only mirror and no, there's no debris located. And these environments are incredibly sterile, so there's no chance of dirt or oil from, say, fingerprints. Even say that's why they're wearing gloves and masks, so that they're when they're breathing, the moisture from their breath does not make any contact, as there's no residue left on the contact of the mirrors. So when the mirrors travel in space, they will not be disturbed by any material resting on the mirrors. And here are some examples of the spacecraft bus system that I mentioned before. Going from top left includes an electrical power subsystem, a communication subsystem on the right, a command and data handling system on the bottom left, and a propulsion system on the bottom right. And there's also a thermal control system, and all these elements have different tasks, have different functions. For example, the electrical power subsystem converts sunlight shining on the solar array into power. The attitude control subsystem provides an orientation of the JWST, so it maintains a specific orbit and points a specific region in the sky, so that the science instrumentation can collect light from a specific source. There includes also the communication system, so all these different components can talk to each other, and data handling system, which serves as a brain for this for the spacecraft, to collect that information and make sense of that information. And then, of course, the propulsion system is required to again move the spacecraft around and maintain an orbit. And all these different systems are put together and are designed to operate with one another to allow James Webb Space Telescope to complete its mission. There also includes various mirror detection systems, two called NIRSPEC and NIRSCAM, that are light collectors essentially. So the light that is captured by the mirror is placed into and redirected in the very specific channels that travel within these instrumentation systems. And these instrumentation systems have channels that magnify the light that's being collected and converted the light, which is in photons, into electrical information, electricity, which is then converted into computerized language and eventually data that can be converted into then the beautiful images that we'll see from JWST. Okay, another breakout session. So based off what we learned about JWST, would any of you like to share your thoughts on astronomy? Is there a specific, so you all had shared different examples of objects in space you'd like to study. Do you think JWST would help us discover some new objects, or would help us learn more about how black holes form or new exoplanets we haven't seen before?
Excuse me, mister, can I share my thoughts on JWST? But I think it will be more like a question actually related to the James Webb Space Telescope. I am actually thinking how to magnitude of the James Webb Space Telescope, because like the shape of its primary mirror, it's not circular, right? Like the ordinary telescope that we have. And if I was wondering, actually, I calculated earlier, if I use the same formula that we usually use to calculate the limiting magnitude of telescopes that usually have circular primary mirrors, the limiting magnitude of this James Webb Space Telescope is around like 20 magnitude or something. And the main purpose of this telescope is to detect the very first galaxy formed in our universe. And based on the Hubble's law, we know that it is believed that our universe is around 13 giga years old, or maybe 14 giga years old. It means that the very first galaxy formed maybe is 13 giga light years away from us. And I also assume that I earlier calculated with using the absolute magnitude of Andromeda galaxy, which is around -21 or something. And I calculated and I discovered that this telescope's limiting magnitude is actually smaller than the magnitude of a galaxy with the same absolute magnitude with Andromeda galaxy at the distance of maybe 13 giga light years. And it's actually kind of interesting for me, since like it's the main purpose of the James Webb Space Telescope, right? So is there any other equations, or maybe how we calculate the limiting magnitude of this telescope is kind of different with the ordinary one?
Thanks, Gilbert, for sharing your thoughts on astronomy. That was some fascinating questions that you have. In the context of a point I wish to, that you made, I wish to comment on, is with regards to the estimated age of the universe and the mathematical calculation of that age based off of information we've gathered from Hubble and its capability to look into the universe and the constraints related with that, as the distance that Hubble can see into the universe is related with how it's designed based off of its mirror system. And the furthest Hubble has been able to look into the universe has been about the age of the universe. I mentioned 13.7 or so billion years, and that's also the youngest that we've seen of the universe, because that's light that we're seeing 13.7 billion years ago. Okay, it's not light that we're seeing right now from that part of the universe, but 13.7 billion years ago, that's finally reached us. But that's also related with one, the type of light, and two, the hardware that's capturing that light. As I mentioned before, with regards to the NIRCam systems that magnify light, there's a hardware limitation with what kind of information we can gather based off how much light we're gathering. And related with that is more specifically how JWST will be able to collect more light than Hubble had in the past. And in turn, we'll gather more information about what Hubble has seen already, but also we'll learn if we can look deeper into the universe and see if it may actually be older than 13.7 billion years. So that's will be really exciting to see James Webb Space Telescope once it's launched. So I think there's some more. Okay,
All
there's a. Sorry, Lovely, go ahead.
Okay, we have another question here. I'm not sure how to pronounce your name, but please go ahead.
Hello, Dr. Sunny. Nice to meet you. Okay, yesterday we make some model from origami about James Webb Space Telescope with my son. And from this perspective, I really want to know about what is the main purpose from the scientists to know more about the origin of life, especially for the modern times like this. I really want to know, feel curious. Thank you.
Thank you for that question, and that's great to hear you've designed a origami version of James Webb Space Telescope. I love origami. It's incredible kind of artwork that can be done with origami. And with the James Webb Space Telescope, there are many innovations, discoveries that this project will lead us to. One, we will learn more about the universe in a way that had never been done before, in a much more detailed, deeper, and more comprehensive manner. James Webb Space Telescope is a incredibly unique telescope because it can gather information in many ways. It can gather information in deeper ways, looking further into the universe than ever before, and it can help answer many questions, from more information about the universe, more information about galaxies, more information about planets, stars, and more information about if there's life elsewhere in the universe. So it will increase our knowledge in many different ways. And in turn, it is also a great opportunity for next generation of space enthusiasts to get involved and help us make sense of that knowledge. As there'll be lots of data that'll be gathered, there'll be lots of information that'll be gathered, there'll be lots of images that'll be gathered, there'll be lots of opportunities to learn about and figure out what James Webb Space Telescope is discovering for us. But James Webb Space Telescope is simply a tool for us, and it can capture wonderful data, wonderful images, but it's up to us to make sense of that information. So it's a incredibly exciting time to be a student interested in astronomy, interested in aerospace, interested in space projects. As the James Webb Space Telescope will open up so many ways to get involved and help us figure out exactly what our universe is and what's in it, and many more different questions.
Okay, thank you for the answer.
You're welcome. Would anyone else like to share your thoughts on astronomy? Well, thank you for those that shared, and for the great conversation. So I'm gonna go ahead and chat a little about how we talked about the rocket systems, the propulsion systems of JWST, and how JWST has to travel in space. And it travels in space in a way that is different from the Hubble and various other telescopes, where here is the Earth traveling on the sun, and then these lines describe different steps along the way of JWST's mission profile. And this includes launch plus various times. So a few minutes after launch includes where a step where JWST is separates from a rocket, and then travels on its own through space, where there include various steps such as its solar arrays being deployed to capture light, and then various elements of it deployed to protect the telescope. And as time progresses, it's also traveling further away from Earth. So WST will not actually be orbiting the Earth, but rather will be orbiting a different location in space, further away, so that it's actually not capturing the light that is reflected by the Earth from the sun to the telescope. So it's in a location in space that is truly actually capturing light from across the universe, and not potentially being affected by light being reflected by the Earth. And here's just an example of 3 different visuals of the telescope traveling through space. We have a couple different views: from the top, from the side, and from the side from the sun. This blue dot here is the Earth, with the telescope moving away and having a very creative flight plan. And one thing to note, wait for these videos to restart, is how fast it's traveling. 0.3 kilometers per second may not be very fast, but a car traveling is, say, 50 or so kilometers per hour, and this is in seconds. So and this is the distance it's traveling from next week up to 2023, when it'll have reached its destination and have traveled over 2 million kilometers. And to provide some perspective of how that compares with, so a trip around the Earth is about 40,000 kilometers. So here we're talking about nearly 2 million kilometers, if not more. And before it is loaded on a rocket, this is what the James Webb Space Telescope looks like. This was at NASA Goddard, but now it's actually located in. This is from it being taken at in Maryland in the United States, but now it's actually located in Florida, and has many different parts to it, including the telescope, the mirrors that we were chatting about, pictured here in a environment that is used to test and simulate the space environment in terms of a lack of air, temperature, and many other factors. Now I'm actually going to share a video of the launch. So 1 second. I'm going to screen share. Okay, can you all see this video? So this video describes the launch to the launch trajectory that I showed some additional visuals previously. Here it is taking off in this video it's the Ariane European rocket, but it'll actually be taking off a rocket in the US. Now the rocket is made into space, and these are the fairings that I described previously being released so that the telescope can be deployed from the rocket. Now it's traveling through space. There we have the solar panels releasing so that the telescope can start capturing light. Now it's releasing multiple panels. And stretching its sun protection shield. And moving towards its final stage and releasing its secondary mirror, fully deploying its primary mirror, and now it's fully operational. And when it's fully operational, I mentioned there will be lots of new knowledge acquired by JWST, and in turn, many opportunities for space enthusiasts to get involved. And here are a few examples that already exist in terms of ways to look at astronomy through citizen science or ground station opportunities. And then stay tuned for ways to be involved with JWST from a citizen science approach, like there was and has been with the Hubble Space Telescope. And it's incredibly exciting because of one, the JWST launching, but also where we're returning to the moon through our Artemis project, our international collaboration effort, and now is a more active time in our space exploration activities than ever before, and more opportunities will. More projects are being launched in space than ever before. There are rocket launches on a weekly basis. And back when I was in college, it was perhaps once or twice a year when there was a rocket launch. But now it's incredible that it's a weekly routine manner of launches now. So I have one more video to share. Never mind. That was now what I meant to share. What I meant to share was a thank you to the JWST team, which many of which are present here in front of a full-scale model of the JWST system in at NASA Goddard in Maryland, and see it's a very large telescope, but it also took a large number of individuals and team members from many different disciplines, from scientists, technologists, engineers, mathematicians, and many more to work together for many years on this really fantastic and exciting, incredible space project. So hope you all can tune into the launch next week. And that being said, I am happy to address any additional questions I may have, and also pass the presentation to the co-presenter for today, Todd Sullivan.
Yeah, all right. Thank you so much for that great and very informative presentation, Dr. Sunny. Oh yeah, so just to remind everyone, we still have another speaker, and then after that, we're gonna have an open forum where you can ask all your questions. But at this point, we can also take another questions from you guys if you have any questions for Dr. Sunny. It could be related to his presentation, or actually could be anything, and even if it's not related to James Webb Space Telescope. All right, so we have one question here from Kelly.
Yes, I have a question about the testing of James Webb Telescope. So does that mean that the James Webb Telescope has never actually been tested live before? It is so big, so I don't think it can be tested, launched, like actually launched for testing. So doesn't that mean that it has a risk of sorry, but malfunctioning at the space actually? So how is that risk being avoided? How can that risk be avoided at space later?
Hi, Kelly. Thank you so much for your question. That is a fantastic question in the context of a question that's asked with every space project. And you're right, many space projects include many large structures and systems that are often not constructed all together and then tested. But engineering approach is to often separate these different systems. I mentioned, for example, James Webb Space Telescope has a power system, has an electrical system, has a communication system, and these systems will all be tested individually. And upon confirmation that these systems work individually, then it is there are also additional tests that can be done to connect these systems to ensure that they're communicating with one another, chatting with each other. And if they do that, then the systems are confirmed to be operating effectively. So that is one strategy for testing, and that can go from small scale to large scale. For example, even the mirror systems, the 18 hexagonal mirrors that comprise eventually the large composite JWST telescope mirror. Each of those each mirror sub element is tested individually, and then ensure that they are as equivalent to each other as possible, because if they're not, then the light that is being collected by each individual mirror is going to be slightly different, and that can cause differences in terms of the images that we see. So there are strategies to test each system independently, and then combine them, and then slowly work the way up to the whole system. But it's often true where, for example, the James Webb Space Telescope, and this is also true for the Perseverance rover and many space projects, where the entire space project in operating all at once does not happen until it actually flies into space.
Hey, Sonny, can I kind of chime in on that?
Todd, please. Yes, do.
So, hi, Kelly. How are you? My name's Todd. So to kind of add on to what Sonny is saying, no, honestly, you can't unfold it, right? You can try your best. You can put all the pieces together, and you can just test it and shake it, and whatever you need to do to it on the ground to make it simulate it's like it's going to be out in space. So if it's on a rocket and you know it's going to shake a little bit, well, you shake it all over the place, right? And you subject it to the colds, right? And you put it in a vacuum chamber, and you put out the wings, you test it, and you fold it, and you unfold it. You put it in a cold chamber, right? And you just make it really, really cold on one side, and then the other side is going to be really, really hot, right? So you subject it to a lot of heat. But absolutely, to your point, there's no way really to practice this. And so you just run it through a whole bunch of simulations. Like Sonny said, you make sure the components run together, you subject it to a lot of heat, you subject it to a lot of cold, you practice folding, practice unfolding, you shake it all you can. If you think it's going to get 1 or 2 shakes, you give it 20 shakes, right? If you think it's going to get cold, you subject it to really, really, really cold. And then to exactly what Sonny was saying, you got all these components, and at the end of the day, you really hope it works.
All right. Thank you so much for answering that question. Do you guys have any other questions? anything?
Yeah, I have a question.
Oh, go ahead. Okay.
Yeah, maybe it's a simple question, but I wonder, as we know that James Webb Space Telescope observes infrared wavelength from, if I'm not mistaken, 0.5 micron to 13 or so micron. Yeah. If we compare it to Spitzer Space Telescope, another infrared telescope that operates in, if I'm not mistaken, again, from 3 micron to 160 micron, I think. Yeah, 160, and it's a broad wavelength range, right? So why James Webb Telescope doesn't operate at longer wavelength range like Spitzer did? Why does it only operates at 0.5 to 30 micron, a relatively narrow wavelength range?
Rafi, thank you for that question. So the wavelengths, though they may be both infrared, capture different pieces of information. And that's related with the sources of the what's releasing light. And there is it's related specifically with relation to what those telescopes, what the objectives of those telescopes are. The Spitzer telescope, the objective of the Spitzer telescope was with regards to, I believe, exoplanets specifically, that Kepler later was the Spitzer's successor, and exoplanets do not reflect as high energy light compared with, say, stars or various other celestial objects. But then JWST is also inclusive of those exoplanets by having a little bit of overlap between that wavelength as well. So James Webb JWST will be able to capture some information about exoplanets, not as much as, say, Kepler will, but some information. But we'll be able to capture more information than, say, the exoplanet telescopes can, specifically with regards to stars, with regards to galaxies, with regards to quasars, etc. And in turn, is the rationale for why they capture different wavelengths of light, which every telescope will. And part of the rationale for why JWST captures infrared specifically, not UV and infrared, let's say like Hubble did.
So in short, it depends on the scientific objectives this telescope will conduct.
Exactly.
Okay, thank you.
All right. Miss Anne, are you speaking? I'm not sure if I can hear your audio. Can anyone else hear Miss Anne?
No, but I think in the interest of time, maybe we'll hold off some of the questions until after the second speaker's session. Okay, so let's move on to the next part of the discussion of the series. So, having witnessed the night sky from many longitudes and latitudes from all over our home planet, our next guest here realizes that we're all continuous explorers, whether it's looking up at the night sky or looking down back at Earth. His specialty is the solar system and its wondrous contents, and as a volunteer of the NASA Solar System Ambassador Program, he's hosted many great talks about space exploration programs at various events and also schools. And as if he's not busy enough, he's also a logistics expert with 30-year experience in various international companies behind him. So let's join him on this awesome journey of space exploration through the James Webb Space Telescope, and please give a virtual round of applause to Todd Sullivan. Go ahead, Todd.
Hey, how's everybody doing today? Everybody's good? All right. All right. So obviously we had some challenges. I really just wanted everybody to see my Christmas tree here behind me. I tried the background thing, but it looked like I got it captured by the Borg from Star Trek. So it wasn't a really good look for me. And sorry, Captain Picard, Locutus, I ain't going there. All right. So let's get started. I'm going to share my screen. All right.
I love.
Oops. Again, so my name's Todd Sullivan, and you know, it's really glad to join you guys again. I'm the guy that did Lucy, the presentation a couple of months ago. It's great to join you. It's great to hear Sonny. Sonny, you have a beard. I didn't expect the beard, man. It was like this nice cleaving, you know, shaved face picture, and you got this beard going. I love it. It's awesome.
Surprise, Todd.
Yeah. So part of my presentation was to kind of set Sonny up. I had some technical difficulties, so we changed reverse course, which is no big problem. So talking about that mock setup, this is actually a picture of me in front of it when it was down in Houston, Texas. So if you look at the little red circle down there, that little guy down there in a brown shirt and khaki pants, that's me. This is an enormous project, an enormous telescope. Even the pretend one, the mock one, it takes 2 big trucks, 12 people, in 4 days to set this up, even though it's an artificial one. And if you look in the lower right corner of the photo, you see a small group of people. Those were the Northrop Grumman guys that I got to have some conversations with regarding the engineering of the telescope. So this was a great day for me several years ago, but I just wanted to get you guys to see that's me. That's the city of Houston in the background, and this is a really big piece of equipment. It's actually, if you were to set it on something, it's the size of a tennis court. And I think one of the videos that Sonny showed you actually said that. So we're going to run through some fun facts. So it's going to have a hot side and cold side, right? You got to protect the mirrors. So the hot side, it's going to be like 100 Celsius, right? And on the cold side, it's minus 233 degrees Celsius. And again, I think you heard that one of Sonny's videos. So you really have to protect the mirror, and that's what it's all about, right? You've got these 5 shields that are protecting this mirror, and the mirror can never ever see the day of light. Literally, you can't see it. So it's got a cold coating. It has 48 grams of gold, and to put that into perspective, 48 grams of gold is about the size of a golf ball. It's not very big, and I'm not even going to try and tell you how thin that is, but you know, 0.00001 centimeter thick. That's a really thin coating. So just imagine the engineering of trying to get a coating evenly with that and evenly across the whole 9 yards. One of the biggest points, and you know, I had just answered a question, helped Sonny answer a question about the you know, practice, right? Practice folding, practice unfolding. You have to think about this for a second. There are 344 single points of failure. In other words, there's been a lot of delays with the James Webb, and I will talk to you a little bit about that in about a second. But think about it, all right? You're gonna have, if you have a checklist, right? Just imagine you got a checklist and you're trying to do something at home, right? You open up a package and you're trying to assemble something, right? And imagine a checklist and each page has like 20 items on it. You're gonna be about 15, 16, 17 pages of instructions. And you need to get every single one of those right for this to be a success. So just imagine that you're an engineer and you're practice unfolding it and you're at point 6. You got a failure. All right, go back to the engineering drawing board, got to figure it out. You figure out that problem. You get to point 22, you have a failure. Now you got to go back. So just imagine the engineering and the practice that if you get point 206 wrong, project's done with. If you're unfolding in space and you get to point 302 and it's a failure, you're done with the project, okay? James Webb's not gonna work. Even if you get to point 343 in the unfolding process, if that point doesn't work, the whole project's a failure. So just think about the engineering involved in that. 344 single points of failure that has to take place. There's no backup, there's no workaround, nothing. 344 steps need to happen perfectly to unfold to get this where it needs to be. So that's a very strong engineering point and something I'm going to reflect on for a while. So I thought this was a really cool comparison. The bottom one, Sonny covered it in his, you know, the Hubble mirror versus the James Webb mirror. It's like 2.5 meters across versus 6.5 meters across. There's just no comparison. And unlike the Hubble, you know, it's never going to be serviceable. Not in our lifetime and not for the life of the project for sure. Hubble is only 570 kilometers above the Earth's surface, so it's not really far out, and it's subject to a lot of you know, radiation, magnetic sphere, and you know, a lot of things that you know, occur in low orbit space. In perspective, the moon's a little over 350 million kilometers, and then the telescope's going to be at 1.5 million kilometers. It's out there. And, you know, just kind of an interesting comparison. Once it's out there, success or failure, do or die. So we all hope it's due, and goes on. So I got a kind of a laundry list of quick facts here. I didn't want to do, you know, 1,000 slides. So let's kind of hit a couple of these. So the James Webb is going to be 100 times more powerful than the Hubble. And as I think this audience knows very well, as I've heard, because you got a really smart crew out there, it's going to be no visible light, only infrared. So we're not going to get those really nice pictures that we're used to with the Hubble. Really hope the public understands that. You know, this big expensive telescope isn't going to get us really the magazine cover photos and newspaper front page cover photos that we've been used to. Also, if you know, you're into metallurgy at all, when metal gets really cold, right, it tends to shrink a little bit. So all the mirrors are very slightly oversized here on Earth. They're gonna shrink just, see between my two thumbs there, they're gonna shrink that much. You know, just think about that. So these are all the engineering concepts that you need to think about. You know, you're going to send a metal up into space and it's cold. It's going to do different things than down here on Earth. You know, I know Sonny covered the 4 primary instruments. It's going to launch from South America. And I thought this was a fun fact. I know here in America, we talk about sunscreen, protecting yourself with the sun by SPF. I'm not really sure how we talk about, you know, sunscreen in other countries, but from my understanding, my language, it's going to be like an SPF 1 million, where like they sell over the counter in pharmacies like 30 and 50 and like maximum 60. This is gonna be like 1 million. 3 primary international agencies are part of the mission, but in all 14 countries contributed. And this was interesting. Each shield is less than a human hair thick each. So that really talks about the delicacy of the mission when it's unfolding. And, you know, something rips, you know, it just creates enormous risk for your overall success of the mission. And the mirrors are made of beryllium. And an interesting side fact, I looked it up. I'm like, hey, where's beryllium mined? Find out that most beryllium is either mined here in the United States or in Russia. And apparently here in Utah, in the United States, is where most of it's mined. So it's a really expensive telescope, right? $4,000 per kilo is approximately what it costs. I couldn't find the actual weight of all the mirrors to get me a total cost. But you know, $4,000 a kilo is about what beryllium costs. And they use beryllium because it's lighter than steel, but it's also stronger than steel. So these are just some of the quick facts I wanted to share with everybody. Okay, so it's been long in the making. You hear different things out there. Oh, it's been in making 20 years, 30 years. I'm more with the 30-year approach. Some of the initial proposals for the Next Generation Space Telescope, which was the former name of the James Webb Telescope, is proposed in 1989. It was approved in 1994. And yeah, I mean, the James Webb Space Telescope is probably going to go down in history as one of the most delayed projects. I can't really think of a project that was delayed more, but it just talks to the complexity of everything. It talks to the engineering, the testing, getting the aeronautics right. It also tests to the money. I mean, these things cost money. And of course, there's politics involved. So, you know, in 1997, they said, "Yay, we're going to launch in 10 years." A couple of years later, like, we're going to delay it a year. A couple of years later, yeah, another delay. Moving forward up into 2005, 2007, the company that was awarded the contract for the telescope got bought out in a hostile corporate takeover. Northrop Grumman, basically, yeah, hostile takeover. They just basically went in and bought up this other company that was awarded the contract. And then again, it goes through a series of testing and testing and testing. So there's something else complex happening right here, right? So there's 2 other things that are happening. One is the rate of technological development, right? Technology that was in early 1990 was not the technology in 2000, was not the technology in 2010, and is not the technology that you have now. So you have rapidly increasing technology, and you want to keep incorporating that into the telescope. So the telescope has an original mission, right? Its focus was deep space. And we're going to talk about in a minute is the rate of discovery of new things. One, kind of changed the mission, changed the focus of the James Webb Telescope. And so additionally, you have that. And so now, not only is your technology changing, but the focus on what to look for is changing, right? So now you're a program manager, you have a delayed project, it's got a lot of cost overruns, it's really expensive. And now you're getting emails and you're getting requests saying, hey, let's go look at this. Hey, you know, James Webb would be really good at this. So now you're a program manager for NASA, and you're way over budget, you're way delayed, technology keeps accelerating, and you're getting all this requests to do different things objectively with the telescope once it's launched. So there's a lot of incredible stress, a lot of incredible pressure to be able to satisfy everybody and all their requests. Keep it under budget as much as you can, keep the focus, develop as much technology as you can, and really change with the changing world, right? So here's a couple, two examples that I'd love to throw out there. First one, the top chart is really talking about exoplanets, and we had just talked about that here a minute ago with Sunny. But really the focus is, you know, and then the lower one is near Earth asteroids discovered. And you can see that in the late mid 1990s, there's an acceleration of discovery, right? So when I was your age, and these are these two red dotted arrows, kind of shadowed in blue. When I was your age, you know, high school, college, things are really, really boring. You know, to Sunny's extent, you know, there is a rocket launch a year. I mean, now rocket launches are happening all the time. And so it's happening not just with exoplanets and asteroids, it's happening all across the spectrum. It's happening, and you know, radio astronomy, X-ray astronomy, gamma, the whole 9 yards. Every field of astronomy is exploding, and almost everybody wants time on the James Webb Telescope. So when the James Webb Telescope was originally being designed and built, it pretty much had a mostly singular dual purpose. But now everybody wants a piece of it because everybody needs access to the high technologies is going. So these are just two examples of one of the reasons why I personally did not get into engineering and didn't become a scientist. And you know, Sunny and I have had side conversations, and we were both like, I wish we were young again. I want to be young again. I want to go back to college. I want to be at college age again. I want to explore all this stuff. And but you know, that's why we're talking to you. And so you you know, the younger generation can get motivated and see this and really get in engaged in it. And everything is happening so fast. So no matter what your interest, a dual interest in botany or geology or oceanography or atmospheric or meteorology or space weather, whatever it is, architecture, whatever your interest is, now there's a need for that in space. Whether you're developing a colony on Mars, 3D printing buildings, architecture, engineering, the whole 9 yards. You don't need to be an astronomer to be an engineer on Mars, okay? Or the moon, or wherever you want to go. You want to mine an asteroid. You don't need to be an astronomer. So we're at that point. Wherever your interest is, it doesn't have to be Earth-based anymore, and that's the really, really exciting times. Like I said, when I was high school and college, things were really boring. Voyager flew past Jupiter and Saturn. Now we've explored these planets multiple times. So now is really a great time to be into this. We had mentioned Kepler here a minute ago. And I'm glad we did. It gave me a little bit of a segue. But I really want to talk about the importance of one of the ways that Kepler really changed one of the fundamental goals of the James Webb Telescope. And if you're not familiar with Kepler, which is great, no problem. Kepler is a recent past mission. So it's accomplished its mission. Some of its interior functions aren't working. The gyroscopes, they had a Kepler-2 mission, which kind of limped along in space a little bit. And but basically, what one of the things that Kepler, it's not really recognized, it's not really talked about. Kepler was a mission to determine future missions. So what do I mean by that? Kepler was a mission to determine future missions. So you have a future plan. NASA has 10-year goals, 30-year goals, 50-year goals, right? And the search for exoplanets many years ago was a big priority. We had discovered a couple, and we were like, oh, wow, will they ever really exist? So the solar system isn't alone in planets. So one of Kepler's goals, one of its quiet goals, was to determine future missions. If Kepler went up and it did not find very many exoplanets, that was going to drive money and budgets and politics in one direction. But if Kepler found a lot of exoplanets, that's going to drive the money and funding and politics in a completely different direction. And that's ultimately what happened. Kepler went up. It looked at this little spot right up there in Cygnus, and it just stared at that spot for 24 hours, 7 days a week, 365 days a year for a little over 4 years. And lo and behold, it found a lot. And they're still going through the data, and it found a lot of planet candidates. And a lot of these have been confirmed. And this is only just using one of 3 or 4 techniques for finding planets. And so you can just imagine, oh my God, what if we apply some of the other techniques? And so after it came out, and I actually did a presentation a few years ago, and I went on to Google, earlier this week, and you can go up and find it yourself. So in the 2013, 2015 range, based on Kepler's data, they estimate there could be as many as 100 billion or 1 billion Earth-like planets in our own galaxy. So that's incredibly exciting. So with this, it really started changing part of the James Webb Telescope's goal. It added to the portfolio. So originally it had, hey, Congress, hey, back in 1995, here's goal number 1, goal number 2, goal number 3. But now the goals are completely changed. Technology changed, the rate of discovery changed. So the story of James Webb Telescope has changed. So this is, I'm kind of honing in towards the end here. Got some photos coming up. So this is, the background radiation, cosmic background universe. So this is really the universe as we know it. And, you got some less dense areas, the darker blue. You've got some super dense areas with the yellows and reds. And James Webb Telescope could fundamentally change the way we view the universe, the way we view the galaxy, the way we view planets, the way we view ourselves. It will probably create more questions than answers. Absolutely, that's how discovery goes. That's what science is about. Answering a question and finding out the answer to the next question is, and so on and so on. Keep asking questions. The scientific process of discovery, and keep learning and pushing the boundaries of what we know and understand. So I really expect that this map, although it is what it is, the space telescope that's going to go up will totally obliterate our understanding of what we currently think that this map is about. So the James Webb Telescope, once it's launched successfully, cross my fingers, hope to die, it's going to have kind of 3 primary missions right off the bat. One of them is going to be Jupiter. they want to use the James Webb Telescope as part of its closer focus to look at the red spot. There's some stuff about the red spot that they just can't figure out, even with all the current probes that have been there, including Juno that's there now. So they're really hoping the James Webb Telescope is going to maybe give some answers. And I think it was, and Sonny can correct me, it was like the 2 to 5 micron range, and don't quote me, but just trying to think of off the top of my head. So this is what Jupiter looks like in infrared. Looks hot. That's what infrared is. It's heat, right? So if you're looking at Jupiter in the infrared, that's what it looks like. You compare that to the visible and the ultraviolet. So what we're used to seeing is the middle photo, and you know, on the right is the ultraviolet. So different wavelengths, different ways to see things, different instruments, but they all provide important clues. And so we're really hoping that the James Webb, with its capacity, can help provide clues, not just for Jupiter, but for other systems as well. And one of the other primary targets early on for the James Webb is going to be the TRAPPIST system. You know, detecting atmospheres. But we're really hoping that we can block out the sun, look at the planet, or planets, 3, 4, 5, over here, block out the sun, and, you know, just kind of focus on these planets. Now, we're used to our solar system that's got 4 rocky inner planets, asteroid belt, some dwarf planets, Ceres, some others. The TRAPPIST-1 system's got 7 inner rocky planets. How cool is that, right? And we think 4 of them are in the habitable zone, right? There's a zone based on the star size, based on the star's heat. There's this zone around that makes it habitable, where we say Earth is. So we're really hoping that, you know, we can look at atmospheres. And again, this is all unproven technology. Well, it's proven conceptually, but we're really hoping we can actually find, right, the next habitable planets. And so, you know, you have a newly forming planet, you know, does it have mostly carbon dioxide? And you find a planet, if it's high carbon dioxide, it's going to be like a Venus. It's going to be like a runaway greenhouse effect. If you find a lot of oxygen and nitrogen, hey, you're likely to have a water world. And if you have nitrogen with the carbon dioxide, you know, if you remember seeing the movie Star Wars, you know, Tatooine, well, you're going to have a Tatooine, right? Livable, maybe. Desirable, not so much. So literally, this is really the expectations that we really hope to get from the James Webb Telescope. Will it find other Earth-like planets? You know, statistically, Kepler tells us there's billions of Earth-like planets out there. Is James Webb Space Telescope gonna find those for us? And that's really the magical question, isn't it? And I know Sonny had a slide or 2 of these. And again, here I've got 2 slides. You got the Hubble Visible Light Telescope on the left, and on the right you have what's an infrared image. The beautiful thing about infrared is that you can see through the dust, right? It's not seeing through the dust, it's detecting through the dust. And you can see so much more of the material that's there in the form of heat, right? It has to give off heat. And so if you look at the 2 images, they're the same point in space, but one's visible, like you and I would see it, and oh, look, you know, the one on the left, I would love to live on a planet near there and be able to look up. Oh my God, look at that in the sky. That would be just so cool just to have that. You know what? I just may paint that on my ceiling. I think that's a good idea. I'm gonna the image that's there on the left. I'm going to paint that on my ceiling. I like that. Honey, we're gonna paint something on the ceiling tomorrow. Just kidding. But you know, you have the image on the right, and that just gives so much more detail. And that's what it's going to give us. It's going to give us a lot more detail. And here's another image, Lagoon Nebula. I don't know, which one should I paint on my, all right, we're gonna have a vote later on. Which one should I paint on my ceiling? The last one, the Pillars of Creation, or Lagoon Nebula? All right, we'll take a vote later. But again, you can see through it, right? And it's not that you're seeing through it, you're detecting through it. You're finding the heat, and it gives you so much more information. The visible one gives you a lot of information. It gives you the structure of the dust and the blows and everything like that. And if you looked at this in X-ray, you looked at this in ultraviolet, you're going to get different pieces of information. But we're really going after the infrared with this project. And thirdly, so first it was Jupiter. You know, that's going to look at exoplanets and deep space. But the ultimate goal initially for the proposal of this is seeing further than what Hubble could see. If you're familiar with the ultra deep field, and hopefully the team has seen stuff like this. You know, can we see back to the origin? Probably not, but it's exciting to think about. But if you understood what we understood commonly about the universe before Hubble and what we understand after, it's two completely different stories. And so the same thing is going to happen here with James Webb. We're going to have a before James Webb, and we're going to have an after James Webb. And the understanding is going to be completely different. And James Webb's going to tell us stuff that's going to change our fundamental understanding. Okay. So if you go back to, like I said, back in the 1980s, when I was a teenager and going to college, the universe was pretty boring. It was pretty static. And technology really drove that. Remember, there's something out there called Moore's Law. You know, technology doubles every 2 years, exponentially. So you just imagine where, you know, you guys are going to be in 20, 30, 40, 50 years. What you're going to know that I never knew. Really exciting times. Now is really the time to be getting into this, because it's just going to keep growing exponentially from here on out. So if you're in high school right now, you're in college, going to college, I'm jealous. I'm really jealous. Now is the time to be in this. And I'm really excited for everybody who's going to be in this. And I remember on the last call, briefly, Ann and I had talked about being multidisciplined. And I mentioned it earlier, biology, chemistry, geology, botany, animals, architecture. We have entered the phase where all of that is needed in space, all of it. They're growing chili peppers. I read an article here a couple of weeks ago. They're making tacos with chili peppers on the space station, right? They had grown these chili peppers, and they brought up the taco meat, the shell. They're cutting up the chili peppers that they grow on the space station. We're growing food in space. We're doing it. Now's the time. Now is when we're going to really grow into this exponentially. And that's what I really have for the team today. This is another photo mock-up of James Webb Telescope, and this is a night shot when it was being displayed outside the University Observatory in Dublin, Ireland. So that's where this photograph was taken, Dublin, Ireland. And here's a night shot of the telescope where it's at there. So I am going to stop. I'm going to turn it back over to the hosts. So if you have a really, really technical question, you say, hey, Sonny. If you have a really generic question, you go, hey, Todd. Okay, go back to the audience over there. How are you?
Thank you so much. All right. Thank you for that awesome presentation, Todd. Yeah, I think it's crazy to think that we might be actually able to detect some Earth-like planets, and there's actually life on other planets. I think that's going to be revolutionary for astronomy in general. All right, I think everyone is already equipped with their JWST facts and information, and I'm also certain our participants has more questions to ask. So let's jump right into the next part of the session. To moderate our open forum with Dr. Sunny and Todd, may I call on Antarexxa's advisor for astronomy, Pak Kunjaya from Bandung Institute of Technology.
Hello, everybody. Hello, Todd, Sonny. Very nice to meet you. I have quite a technical question. Yeah, I'm wondering how James Webb Space Telescope can take spectra of distant galaxy and quasars. It is taken simultaneously or one by one, or how? And how faint a galaxy can be observed by the JWST spectroscopically? Thank you.
Sonny, I'm going to let you kick off on that one.
You got it, Todd. Yes. So with regards to the that's a question specific to the scientific instrumentation on board JWST. And there are multiple. The ones I'm particularly familiar with are called visuals of are called the NIRCam and NIRSpec. Both stand for near, then NIR stands for near infrared, then cam is for camera, and then spec is for a spectrograph. And the camera is, once light is captured by or is reflected by the primary mirror onto the secondary mirror, then that is reflected onto the scientific instrumentation bay, which includes NIRCam, which is an imaging system that covers a wide spectral range specific to JWST. From my notes, I recall the range being 0.6 micrometers to 5 micrometers. And there is also a megapixel equivalent. So like a phone camera or any camera, there's a certain number of pixels that are captured a certain resolution, with the NIRCam resolution being 4 megapixels. Though this is different from, say, a light camera that maybe 8 or 10 megapixels. It's not the same, but though the quantity of pixels can be comparably equivalent. And this is actually a instrumentation system developed by Lockheed Martin. So if one is interested in learning more about the specifics of with regards to how this system works, there is more information available by Lockheed Martin on the NIRCam system. Now, to describe so that's the camera system. Then there's the spectrograph, which takes this information captured by the camera and across a certain wavelength, and converts that information into what are called spectrographs, which take the pixel information and present it across spectrums which relate to specific objects. And there are different filter mechanisms, there are different gating mechanisms that take this data and specify it to specific objects that are then integrated and then are converted into the optical images that are eventually captured. The NIRSpec system was not actually created by Lockheed Martin. It was created by Carl Zeiss, which is a very famous optical manufacturer, microscopes and many other imaging systems. And there, I'm aware there are additional. So those are the near infrared systems. There are also mid infrared instrumentation and additional spectrographs that provide a lot of functionality and gating and matching the information, because even though 0.6 micrometers to 5 micrometers for the NIRCam may not sound like a very a broad range of light being captured. It's not just the range, but also the source, and it's in particular the source that is the universe and everything that's contained in the universe across a specific range. So the range could be increased, say from 0.6 micrometers to 10 micrometers, but in turn that could actually increase signal to noise ratio. So the images, the data being captured is no longer actually actual signal, but could just be background noise that may not have any not importance to it, but maybe outside the specifications of the specific hardware system. So there's a lot of customization and thought certainly put into the specific ranges that are being first captured and then converted into data and then interpreted.
Okay, thank you. One more small question. Is there any possibility for astronomer outside the consortium, outside US, Canada, Europe, or 14 contributing countries, to propose an observation? Is there any such possibility?
So this being not not within my field, I'm unsure. I do recall there being citizen science opportunities through Hubble Space Telescope. So I speculate there may be similar. Those are the mechanisms I'm familiar with, but that's not to say that there are not ones out there for astronomers across the world to propose for. There may be. I'm just not be familiar with them.
Okay. Thank you very much. It is very sophisticated instruments. So I think everybody is waiting for many surprise given by Webb Telescope. Thank you very much.
Thank you for your questions.
All right, thank you so much. I think we have 2 more questions. Okay, let's go ahead with Jung. I'm not sure if I'm pronouncing your name right.
Yes, okay.
So sorry.
I have 2 questions. The first one is, what else is beryllium used for other than a telescope? And the second one I have is, I made this telescope, but the bottom part is pink colored. And why is it pink? Just asking.
So I'm not aware of the pink color. That's a surprise for me. If Sonny, you have anything on that? I mean, hey Johnny, I remember you from the Lucy talk, and I don't know if you joined.
We've met.
Yeah, I don't know if you joined Sonny with the Dart one, but I remember you from the Lucy talk. Is that mom or is that sister? Yeah, I don't know of any specific other uses for beryllium. I know it's being used more and more, but it's expensive, right? And personally, you know, I'm just being honest, I'd have to go online and look for other uses for beryllium online. But you know, it's a steady. I'm trying to think. There is a YouTube, hold on a second. There's a YouTube channel out there, and it has 3 parts, and It might even be the James Webb Telescope YouTube channel. And I think they talk in 3 different parts about beryllium, how it's mined, how it's refined. And that's actually where I got some of my information. But it's actually a powder form. So getting into a solid form is actually kind of hard. But once you can do it, it's very strong and lightweight. As far as the color is concerned, you got me on that one. I don't know if Sonny has anything to add to that.
Doug, thanks for your great questions. Beryllium may be the may have a alloys, and those rare earth metals all have a unique. Talking about spectrographs earlier, have unique spectra, which refers to what kind of light they reflect. So it may be unique to beryllium. I'm not familiar with beryllium, though that may be the start of a really fascinating research project for you to research and explore what use beryllium has for space projects. Maybe with telescopes, maybe with rockets, maybe with, who knows? Up to you to discover that.
So,
and please let us know what you discover.
Yeah, I want to know. I want first in on that.
I'm fine with second.
It's also used for medical imaging. So it's used in medicine.
Oh, really? Awesome.
Yeah. So it's semiconductor, and then it's highly used in medicine. So Sunny, it will be a new avenue for you to look into as well, because it's used in imaging equipment, diagnostics, laser medicine. It's
awesome. I love to hear more space spin-offs translating into medicine. So that's
absolutely.
Thanks, Young, for teaching me that.
Absolutely. Yeah, that's great information. Good question. Good follow through. I learned something. Sonny learned something. I love sharing.
All right. Thank you. Thank you for that question. I think we have another question earlier. Syed, was it you who raised your hand?
Yes.
There.
Sorry, I have to turn my
Where
camera
are
on.
you? Can you turn your video on, please?
Okay. So actually, this is my friend's asking, but she's too shy, I think. First of all, maybe I have to greet Pak Kunjaya, because he is one of my lecturer in ITB. Where's Pak Kunjaya?
Okay.
He's missing, I think. Maybe he still remembers me. Oh, he's missing. Yeah. So yeah. So yeah, her question is actually Hubble was produced what is called Hubble Ultra Deep Field, right? As we know. Can we expect the same image from Webb, and how it will be differ from the Hubble's?
I can start that off, Sonny. You can finish it. So yeah, I mean that's part of the whole focus, right? Can we replicate it? Sure, we can do the same thing, but we can do it in infrared as opposed to visible. And I believe part of that actually was infrared, has some capacity. But really the goal is not just to replicate it, but to go beyond, right? So Hubble can only see so far, see so deep. And so the idea is, this is high level, but Hubble basically looked at a dark spot, stared at it, and found a whole bunch of stuff. So now just imagine kind of James Webb going into the ultra deep field, finding a dark spot, and then reimaging a whole new universe behind that. So the whole idea was to take, if you're familiar with the term or philosophy, is standing on somebody else's shoulders, right? I'm only as good as somebody before me. I'm standing on their shoulders. And that's kind of what this is, really is. James Webb is really going to stand on the shoulders of Hubble and, bring it to a whole new level. Sonny, your take on that?
Yes, Rafi, thanks for that question. Certainly, in the context of, we learned a lot from Hubble, and we'll build on that with JWST. and also it's related with innovation and advancement in technology and capabilities. Hubble was designed the way it was back in the 80s, 1980s and 1990s, based off of the tools available at that time. And JWST built off of that and evolved off of advancements made in many different areas of science, technology, engineering, arts, and mathematics, to enhance, to expand what we've learned from Hubble. So JWST will certainly, based off of the innovations made and lessons learned from Hubble, we learned a lot, not just from Hubble, but also through the development of Hubble, of how to design JWST. And in turn, Hubble also, as any hardware system, as any tool, every hardware system will eventually break down and can no longer be repaired. And Hubble, unfortunately, Hubble exceeded expectations many times over, in terms of, in many ways, but in particular how long it's been in service. And that is a key difference that Todd had pointed out with regards to capability we will not be able to have with JWST, where based off of where it's will be located, we will be, based off of current means of, so that's another a potential opportunity for innovation and in service or in space remote servicing of JWST. But to answer your story, to answer your question more specifically, Rafi, we will look beyond what with JWST, what Hubble has shown us, and we will also learn in greater detail, and we will learn from a broader perspective as well. But certainly JWST would not be where JWST would not exist without Hubble in the first place.
Can I ask one more question? Last question for me. Okay. So regarding JWST scientific objectives, it said that regarding exoplanets.
You can ask a question if your friend is not blurred.
So, actually, this is, her name is Elika. Maybe Pak Kunjaya knows him. Pak Kunjaya, this is Elika. Greetings from her.
Hello,
yeah. Elika, Rafi.
Regarding exoplanet scientific objectives, it is said in those that JWST will observe especially the exoplanet atmosphere through maybe transmission spectroscopy, right? But will JWST detect new exoplanets too, like Kepler did, or is it just observe the atmosphere?
Sunny, go ahead.
So thanks, Rafi, for that question. Exoplanet research is very, very challenging, as there are various various approaches to approach that. Kepler and Spitzer, to my understanding, used a method where they observed the stars of and then multiple stars, many stars, and over periods of time watched if there were shadows that developed periodically and consistently across those stars, as well as measuring if there were any modest shifts in the location, as planets have mass, and as they orbit, they actually will cause very modest vibrations in the position of stars. So that's a gravity-based technique that one of the telescopes, I believe Spitzer actually has implemented to observe exoplanets. But the challenge really with light-based or gravity-based, and also this is true for JWST, is that stars emit a lot more light than planets do. Planets don't emit light; they reflect light, and they will reflect light that the stars will, and will lead to distortions of that light because of their atmospheres. And that's why when Kepler or JWST will measure near infrared for those specific exoplanets, generally when there are distortions, that causes a loss in energy of light. So the wavelength it leads to wavelength shift, and the wavelength that exoplanets will have will be different, further away than the infrared that would be emitted by a star. So now the question is, which so I'm not an expert in this area, but my question in return is, if JWST, the window of infrared that it is collecting captures that window precisely in terms of what the infrared wavelength that exoplanets are releasing, so to speak, are refracting, and some of that knowledge, some of that specification decision making, I presume, was determined based off of the findings from Kepler. Kepler discovered a lot of exoplanets, and then based off that information, collect a lot of information, what kind of infrared, what kind of spectral patterns those exoplanets have, to provide some information as to, okay, what next design can we use to capture more information about exoplanets. And I presume that's also was included with the design phase of JWST. But JWST is a multi-objective telescope. Its focus is not just exoplanets, but it's also stars. It's also looking deeper into the universe. So there are pros and cons to each of those objectives that may have an effect on what sort of information can be gathered. So my short answer is that I hope and would like to see JWST capture a lot more more exoplanets, and we'll just have to wait and see.
Okay, thank you.
All right, thank you so much. Great questions really does yield great answers. And actually, we have another one from Zach. Are you there? He's a 9-year-old. He has a question.
Yes, I have a question. So why is the shape of the satellite mirrors, I think, is a hexagon?
Go ahead, Sonny, you can take that one. I have my answer, but I think you're gonna have a better one.
Well, I think the NASA and ESA and the space engineers, just like the honeybees or something along the lines of them, that's what inspired them to think of. But I in the context of I actually don't know what the rationale for I speculate it's due to the configuration of being able to take multiple units and increase surface area, and perhaps I jokingly refer to honeybees and honey chambers, but that could be an inspiration from nature, where many engineering designs are inspired from nature, and in terms of geometry and in terms of what effectively and efficiently can be put together to to design something. So there's a lot of mesmerizing and beautiful work from inspired in engineering inspired by nature. So perhaps JWST was as well.
Okay, thank you.
All right, Todd, do you want to add something to that?
You know, I completely concur with Sunny. So there's a couple of other components that I think kind of, I can't specifically go to the hexagon shaped figure, but you know, one, you couldn't really do something in a complete solid object, right? So you have the Hubble, you have this 2.4 meter disk. It's just one solid complete unit, right? There's no way to launch something this big that couldn't be foldable. So you can't fold a mirror, right? You got one big mirror, you can't fold it. So it has to be somewhat sectional. And I completely concur with my colleague Sonny on probably some inspiration from nature. But the other thing is too, is since it's going to be sectional, and the thing we have to realize is that on the back of each mirror, there's many motors. So it's not just gonna fold and all come together perfectly. It's just unrealistic. So to help compensate for that, each one of these mirrors is got a whole bunch of motors on it, right? And you know, it's going to take time for NASA and the other organizations just to like tweak, and then eventually get the mirrors where they need to be. So, you know, and like I said, you can't have a solid disk. It's just too big to launch. So you need something that's sectional. You need something that can fold. And then you need something once it's unfolded, it's unrealistic to expect that everything's just going to come together perfectly the first time. So like I said, you've got all these actuators and all these little hydraulics behind each mirror, and they're going to slightly tweak every mirror until they can finally get into the proper configuration. And also remembering, like we said, you know, they're slightly oversized on launch. So as they get colder, their size may change a little bit, which is also a good reason to have these motors and actuators. Yeah, you needed something that's foldable, you need something that's movable, and you need something that you can adjust, because we learned from the Hubble, you know, we launched this big mirror, and you know, if you know your history, the images came out blurry. So we needed to service it and we needed to correct its vision. Well, the James Webb Telescope is not serviceable. So we have to build in the foresight and the knowledge that we may need to correct something. And so I think that's also a contributing factor for the sizes and the shapes.
A quick add-on to what Todd mentioned with regards to comparison to Hubble. So Hubble had also only one mirror. JWST was designed purposely so it had 18 separate mirrors, so that if there was an issue or a potential problem with one of the mirrors, there's the 17 others that could still function. So there's an engineering that's termed redundancy. With the Hubble mirror, there's the one mirror. If there's an issue with that one mirror, which there was, then there's no redundancy. There's no backup. With JWST, there's 18, so there's a lot of redundancy. So that'll also in turn increase the how long the telescope will be able to capture images too.
Okay, thanks. Answer.
Good question.
Thank you, Zach. Does anyone have any other question?
I'm actually quite nervous for James Webb because of the incident. I don't know if every one of you realized, but they had an incident during the delivery. I think they're trying to move it to the adapter or something, and then it shattered the whole telescope. So I can only imagine how does the team feels after $10 billion and 30 years in the making, and suddenly just before launch, they were trying to move it, and it created vibration to the entire telescope. Because what happened with Hubble, right? It was broken, and then it took them forever. Like the senator was not happy about that. Like they have to fix it. So, any updates from that, and how does a vibration, like compromise? What would be the effects of it once it's launched, do you think?
I'll chime in just very quickly. There's so many unknowns, so many variables. It could have done something completely unknown to some other part of the instrument. I mean, there's just so many unknowns. That little joggle may have affected, single point unfolding point, 256 or something. So, and I'll let Sunny chime in, but I will share that I'm in some Facebook groups, astronomy based, and there's a lot of chatter about this being one of the most terrifying moments in a scientist's moment when that thing gets when that rocket booster goes. It's going to be so terrifyingly like. There was one joke where I was reading online. Again, this is a Facebook group, and he's like, "I just hope I don't have a heart attack when that thing takes off." It's going to be a terrifying moment for a lot of people. But as far as probabilities, like I said, there may be something, that incident may have done nothing, and could be something else completely different wrong with it that we haven't detected. So. That's kind of my take, but I think the scientific community, astronomers in general, they're gonna all kind of watch it like this. We're all gonna be kind of like watching through our, our fingers, hoping that it's all right. But it's gonna be terrifying, at least for me, to watch that thing go off. I'm gonna be devastated. Sonny?
Yeah, every space project is kind of like a game of Jenga, where the Jenga is this game where you have blocks, and you put the blocks together in a tower, and every part of the project is kind of like taking a piece of Jenga block away. And as you get closer to the project conclusion, it's having more blocks removed, and it's teetering, and it's really an engineering design question. Have we selected the appropriate blocks and placed them on top to continue the project, or have we picked the wrong one and perhaps set the tower to collapse? And engineering design is a little bit like that. And Todd highlighted how there are many. There are failure points. There's a risk. Everything could have been perfectly fine with the JWC. That instant could not have happened, but then it goes on top of a rocket. Okay, something could happen with the rocket, or the weather, which has delayed the launch already, may continue to delay the launch. Space projects, there are many factors throughout the project cycle. I think it goes back to as a scientist, but also an engineer. I appreciate JWST's the opportunity it provides as a scientific tool. But as an engineer, I understand also the design and how hardware systems and software systems are inherently designed so that they can handle risk, and that they have what are called tolerance levels. And the question is if that incident fell within the tolerance level of that of the hardware that JWST is. So it may have vibrated. It may have had a incident to our observation, but I trust the hardware. I trust the hardware can withstand that instance, as it's going to be launched into space, an environment that is harsher than any environment here on Earth. So if it's handled, if it can handle that environment, it should have built-in tolerances to be able to handle. Not that those are, it's not that that incident should have happened as part of any testing phase, but I speculate the hardware can. I'm optimistic that it's fine and that it can still perform to what it's asked to do. So looking forward to launch and seeing the beautiful images that we'll see of our universe from JWST.
How long until the data? I wonder if anybody got fired from the incident. That's huge. How long until it can relay data?
I'd love to know the answer to that question too. I'm anxiously waiting.
Are you gonna have a hand on it? Oh, actually, Pak Kunjaya asked that question. So Leonardo, you raised your hand up. Did you want to ask?
Yes, I'm sorry if you have mentioned before. So a simple question: that how long the GWST is expected to last in space? Pretend if it works properly, there's no problem and so on. Will it last longer than the Hubble space? Thank you.
I read it was 10 years.
Yeah, so, and again, you know, in Sonny's work on the projects, he's probably got some more interesting details, but yeah, it was supposed to be 10 years. So there's two factors, right? One is if it's a really perfectly operating piece of equipment, those missions get extended. They typically get extended because you're not going to, you know, throw away, not that you're going to throw away the space telescope, but you're not going to stop using an instrument just because it's got its lifetime, right? So if it's still functioning, they'll extend, you know, the lifetime of the mission. So to kind of answer the second part of the question is, you got to remember, Hubble was serviceable. You know, they sent a handful of missions up to upgrade its cameras, upgrade its technology, upgrade its wiring. You're not going to be able to do that with the James Webb. So the Hubble was designed specifically to be upgraded in orbit. So that's one of the reasons why you have the as long as the Hubble lasted, and you're not going to be able to do that with James Webb. So if it's still working fine after 10 years, have to believe and I have to expect that they're just going to extend its mission life until you know, it's no longer functioning or runs out of fuel, right? Sonny, your 2 cents?
Yes, 10 years is the expected project timeline for JWST, and many of those are projected. Those evolve and adapt, and like the rovers and orbiters and the probes like Voyager that traveled deep into space. They are constantly being communicated with and are evaluated in terms of hardware software checks related with the status of the hardware software, and then that allows for, so there will be ways to communicate JWST and adapt the configuration of the hardware and the data acquisition, and those little adaptations allow modifications to increase the lifespan of projects. But then there may be more catastrophic faults that may not be repairable. It's a harsh environment. Deep space where JWST is, it will be constantly bombarded by meteorites, by radiation, by it will not be protected by the Earth's magnetic field, so it will be experiencing deep space radiation, and that has an effect on electronic systems. And then in turn, also the sun has periodic what are called corona flares, and those are also higher levels of radiation that can swamp the JWST system. And I mentioned radiation because radiation has a charge to it, and charge is very important to electronics. And this system is entirely based off of electronics in terms of capturing light, but then converting that light into electrical information. Of course, JWST has shielding, and the hardware systems are designed, especially designed to handle radiation exposure. But those again also have thresholds and limitations, and may have an effect on those will have a greater effect on the lifespan of this hardware more than anything. And we have not had we have had probes, and we've had various systems travel in space, but not like JWST. So there's also a bit of an unknown with regards to the lifespan of the telescope that we'll also have to discover, and will be important knowledge as well in terms of future missions too.
Okay, I think we can take on another question. Last question, I think, for this session.
Last round of question, because it's already very late for Todd and Sunny. Yes, it's midnight there.
Ferdinand, I think, has a question.
Yeah, I want to ask, like, I believe the GWST is in second Lagrange point, right? And I want to ask, like, why is it placed there out of all places? And like, I believe from what I saw in the little GIF, that it has like a small orbit there in the second Lagrange point. And I want to ask, well, why did it made it? Why did they make it like so they have a little orbit there, and what exactly it's orbiting?
Go ahead, Sonny.
Yes, with regards to the orbital mechanics, there are multiple what are called Lagrangian points, which are which serve as Todd pointed out 5 as gravity sinks, where any object in those locations will maintain a fixed orbit around the sun, and there are L1, L2, which are equidistant relative to the Earth, and then L3, L4, and L5 are further away. But please, I don't have those memorized. But Todd, correct me if I'm describing it incorrectly. But the benefit of those positions is that a spacecraft can travel there and no longer rely on propulsion to maintain its orbit, and that is critical for a large object like JWST, but also for its positioning and being able to reorient itself. Once it travels to this position in space, it can prioritize its limited fuel, which it can't be refueled, to have that fuel remaining being focused towards repositioning itself, so it can study the universe versus rather constantly shifting its orbital positioning and burning its fuel off for that. So that is which it also couldn't do well on. If it were, that's what Hubble had to be constantly refueled. So that was also another rationale for why JWST was decided to be placed at this Lagrangian point versus orbiting the Earth. It's a much larger telescope than Hubble, so it would have required much more fuel. So a little bit of a pro and con there. And I also wish to quickly comment with regards to the question of data availability. I love scientific news media announcements, but I do prefer for scientific results to look at the scientific literature. So I will actually share a journal that in the chat, and also as a follow-up, I'm happy to share more examples of one journal. There are many. So in scientific literature, there are many what are called journal publications, kind of like magazines. There are different magazines for different topics, and there may be dozens of magazines for a specific topic, and that's true also for scientific journals. There may be a specific topic that has many different types of journals. So what I placed in the chat is one astronomy journal that a lot of the results from Hubble were actually published in this journal. So if you're really interested in looking at the scientific information from Hubble, this journal will have that. And also, I speculate the findings from James Webb Space Telescope will be presented in this journal, and then a really fantastic science communication site that I speculate would also present future very quickly JWST findings is publicly is Science Daily. I've also placed it in the chat, and it's a fantastic scientific news source. I've been following it for years. It was something that inspired me to get to learn about science, and it has topics on really any scientific topic, and then also even just today or more recently, NASA had a probe that touched the sun, so to speak. It already has information and data about the findings from that study. So I speculate James Webb Space Telescope findings will also be presented here. So I wanted to mention that before I forgot.
And I also want to do some announcement. So for everyone who participated here, thank you for joining. This is our last session of the year. Todd and Sunny, you've been a champion for being our educator this year. Thank you so much. For DART and Lucy mission, hopefully next year there will be more exciting sessions that we can do as well, because upcoming is Moon Camp, right? So Artemis 1 is launching on February next year, which is literally like just a few months away. And we are preparing our Moon Camp in January and I guess that's during the university school holidays as well. So we really hope you all can join us. And there'll be some for everybody. There'll be activity sessions as well. We have a wide range of sessions, but specifically talking about the moon and Artemis 1 mission, moon rockets, moon spacecraft, and lunar robotics, space architecture, lunar habitation model. So how are we going to live on the moon? What kind of house? We are also going to have a session on space food, microgravity research on space food, and space nutrition. So there's a lot of many different kinds of sessions that is going to be prepared for the Moon Camp. So join our Telegram group and our WhatsApp groups to get updated, and also our social media. We'll be announcing the session soon, and register. Thank you, Lovely, for co-hosting today from SEDS Philippines. Unfortunately, our two other co-hosts are experiencing very, very bad typhoon last night. And
then forgot the picture.
Yeah, we'll take a picture soon. So we send our thoughts to Quinn and Dr. Mary. I hope they're okay, and I hope their families are, safe, and they can locate their family during this typhoon. It's been really bad if you've seen it on the news. And so can we take a picture? Can everybody turn on their video and take a picture for our last get together of the year? Just waiting for everyone's video. And I hope you've enjoyed joining our session this year. I hope you all learned something, gain new knowledge, because it's not every day that you can, have access to our brilliant space educators from the US, gain insights from NASA researchers. So make use of this opportunity. And more people coming up. And let's take a picture now. There's two sides. So smile. Next, we are going for the next page. Muhammad, PD Buddy, Devendra, I see you. Next, smile. There you go. Can we have a backup just in case? Let's do another one. So who's on this screen? Kelly, Audita, Kartika, hi. Syed, Rafi, Nico, Ibnu, Devendra. Okay, cool. And on this one is Bruce Anthony, Khairul, Piribadi, Ibnu, hello. There you go. We took our picture. Thank you so much. And I hope you all will have a very good holiday, Christmas. For Todd and Sunny, I don't know, you both still working, especially Todd, because you're in logistics. So Christmas, I'm sure you're overworked.
Yeah, so I'm sure everybody is familiar with the clothing and sneaker company called Nike. Everybody knows Nike shoes. So I'm in a brand new e-commerce facility, and we're experimenting with robots. And we've got 300 robots roaming around the warehouse.
Wow.
And yeah, it's quite interesting to see bot jams, robot traffic jams, and all sorts of things. So everybody's ordering their Nike shoes, their Nike hoodies, and everybody's getting ready for Christmas. So yeah, busy time of year for me.
Yeah, I'm sure. Sunny, are you going to take any time off from research, or are you?
Yeah, soon actually. We are soon to finish a NASA biomedical study, actually this weekend. Looking forward to some time off after that, and then restarting our in the new year, looking into detail with our results, and really excited for this study. Though having to do a bit late in the holidays is a little challenging, but some exciting scientific studies that will be very important for our astronauts when we return to the moon. And then this is, again, thank you again for the invitation. It's been really a lot of fun, and I really appreciate the audience interaction and the questions and the enthusiasm. And it's an incredibly exciting time to be involved with space exploration across the world in a way that I wish it was like that when I was in school or in college. So thank you again. I look forward to seeing you all in the future.
Thank you, Sunny, for spending your time with us on your busy research schedule. And Lovely, thank you so much as well. And
thank you for having me.
and looking forward to more collaboration with SEDS Philippines. And you know, I think a lot of students here also still don't know what SEDS is. And you know, next year we will invite all the big groups from SJC, SEDS, so we can start introducing all these space organizations to the space enthusiasts here. Thank you for everyone who joined us for the first time. And I know there've been like regular faces here, of course, Titan and Mom, and then Leonardo as well. So really, and Rina as well, hi. And I wish you all a very, very happy holiday. If you can have some holidays, I need some holidays. And yeah, hopefully see you again sometime soon. Just keep us just keep updated, and Moon Camp should be really good. We've got a lot of interesting speakers, and Artemis 1 is, of course, it's gonna be the start of a big milestone for us getting back to the moon. So yeah, very exciting times for kids and everybody else who is living in this century. Yeah, I mean, there's just, it's going to be very different from during our time growing up. Keep inspired by space and learn more, and I'll see you soon. I'll see you next year. Thank you so much for your support. Merry Christmas for those who celebrate, and Happy New Year.
Thank you, everyone.
Thank you, everyone.
Happy
Thank you,
holidays, Happy
Todd.
New
Thank
Year.
you, Sunny. Merry Christmas, everyone.
Merry Christmas, everyone.
See you soon.
Thank you. See you at Moon Camp.
Thank you. What time is it in the US? Oh, what time is it with you guys there? Midnight, huh?
Yeah. All right. Okay. We'll end the recording here.
Yeah.